Ground fault protection is addressed first. The fault current, denoted as F, is equal to the line voltage divided by the ground fault impedance, Cf. The ground fault impedance, Cf, is equal to the resistance of grounding conductors plus the resistance of equipment grounding plus the resistance of the grounding electrode. The maximum ground fault impedance, Cf, is 25 ohms for 120 volt circuits and 12.5 ohms for 240 volt circuits. Next is short circuit protection. The fault current, F, is equal to the system prospective fault current, ISC. The system prospective fault current, ISC, is equal to the short circuit interrupting rating, SCCR, of the panel board or main service entrance. Addressing branch circuit protection, the overcurrent protection device, OCP, rating should be less than or equal to the ampacity of the circuit conductor. Fuses or circuit breakers should be selected with the appropriate time delay or trip characteristic to prevent nuisance tripping while allowing for proper fault protection. Open circuit protection is next. Open circuits occur when the circuit path is interrupted or disconnected. Open circuits are typically protected by branch circuit fuses or circuit breakers. Branch circuit disconnect requirements are also important. Article 422 of the National Electrical Code, NEC, requires disconnect switches or circuit breakers for firstly, all lighting outlets except for attachment plugs which are receptacles, secondly, appliances rated over 300 volt amps, thirdly, fixed motors over 1 horsepower, and fourthly, all permanently connected loads. There are additional notes that are important to consider. The requirements will vary based on the specific application and local codes, so it's important to consult the relevant codes and standards. Electrical professionals, such as electricians and engineers, are qualified to provide accurate and up-to-date information on these requirements. It is useful to refer to the National Electrical Code, NEC, Article 210, Article 220, Article 240, and Article 422 for detailed requirements. Understanding ground faults is crucial for electrical safety. A ground fault happens when electricity strays from its intended path and finds an unintended route to ground. This can occur due to damaged insulation, faulty wiring, or equipment failure. The path to ground could be through a person, which presents a severe shock hazard. Ground fault protection devices, like ground fault circuit interrupters, GFCIs, and ground fault equipment protection, GFEP, are designed to detect these faults and quickly disconnect the circuit, minimizing the risk of injury or damage. GFCIs are commonly used in residential settings, particularly in areas with moisture like bathrooms and kitchens, while GFEP is often found in industrial and commercial applications to protect equipment. The impedance of the ground fault path plays a critical role. Higher impedance reduces the fault current, potentially preventing the protective device from tripping quickly. This is why the NEC specifies maximum ground fault impedance values to ensure effective protection. Regular testing of GFCIs and GFEP is essential to confirm their functionality. Short circuit protection is another key aspect of electrical safety. A short circuit occurs when there is an unintended low resistance path between 2 points of different potential in a circuit. This results in a very high current flow, which can cause overheating, fires, and equipment damage. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the circuit when the current exceeds a safe level. The interrupting rating of these devices must be sufficient to handle the maximum available fault current at the point of installation. This is known as the system prospective fault current, ISC. Branch circuit protection focuses on safeguarding individual circuits within an electrical system. Each branch circuit should have an OCT with a rating that does not exceed the ampacity of the circuit conductors. This ensures that the wires are protected from overheating due to excessive current. The selection of the appropriate fuse or circuit breaker involves considering the specific characteristics of the load connected to the circuit. For example, motor circuits often require time delay fuses or circuit breakers to accommodate the inrush current during startup. Open circuit protection deals with interruptions in the circuit path. While not as immediately dangerous as short circuits or ground faults, open circuits can disrupt the operation of equipment and systems. Fuses and circuit breakers also provide protection against open circuits by de-energizing the circuit if a fault occurs that leads to a sustained low current or no current flow. Branch circuit disconnect requirements are outlined in Article 422 of the NEC, which specifies the need for disconnect switches or circuit breakers for various types of equipment. This allows for safe isolation of the equipment for maintenance or repair. The disconnect should be readily accessible and clearly labeled to indicate the equipment it serves. For lighting outlets, individual disconnects are not typically required except for specific types of lighting fixtures or in certain commercial and industrial settings. Appliances rated over 300 volt amps, such as water heaters and air conditioners, must have a dedicated disconnect. Fixed motors over 1 horsepower also require a disconnect, which can be a switch or a circuit breaker. Permanently connected loads, like electric heaters, also need a disconnect for safety during servicing. In addition to the NEC, local codes and regulations may impose additional requirements or restrictions. It is crucial to consult with local electrical inspectors and authorities to ensure compliance with all applicable codes. Working with electricity can be dangerous, and it is essential to have the knowledge and skills necessary to perform electrical work safely. If you are not a qualified electrician, it is best to hire a professional to handle any electrical installations or repairs. This ensures that the work is done correctly and safely, minimizing the risk of electrical hazards. The NEC is a comprehensive document that provides detailed guidance on electrical installations. It is updated every 3 years to reflect changes in technology and best practices. Staying up to date with the latest edition of the NEC is essential for electrical professionals. Understanding the principles of electrical safety and code compliance is crucial for protecting people and property from electrical hazards. By following the guidelines outlined in the NEC and consulting with qualified professionals, you can ensure that your electrical systems are safe and reliable. Consider the impact of harmonics on electrical systems. Harmonics are distortions of the sinusoidal waveform of alternating current, AC, electricity. They are caused by nonlinear loads, such as electronic devices, variable frequency drives, and some types of lighting. Harmonics can lead to a variety of problems, including overheating of equipment, increased energy consumption, and malfunction of sensitive electronic devices. To mitigate the effects of harmonics, various techniques can be used, such as installing harmonic filters or using equipment designed to minimize harmonic generation. Power quality monitoring can also help identify and address harmonic issues. Surge protection is another important aspect of electrical safety. Surges are transient overvoltage events that can damage or destroy electronic equipment. They can be caused by lightning strikes, switching of electrical loads, or other disturbances on the power grid. Surge protective devices, SPDs, are designed to divert surge current away from sensitive equipment, protecting it from damage. SPD should be installed at the service entrance and at downstream locations to provide comprehensive surge protection. Regular inspection and maintenance of electrical systems are essential for identifying and addressing potential problems before they lead to failures or hazards. This includes checking for loose connections, damaged insulation, and corroded components. Thermographic surveys can be used to detect hotspots in electrical equipment, which can indicate potential problems. Electrical safety audits can help identify areas where improvements can be made to enhance safety and code compliance. Education and training are crucial for promoting electrical safety. Electrical workers should receive comprehensive training on safe work practices, hazard awareness, and the proper use of personal protective equipment, PPE. Ongoing training is essential to keep workers up to date on the latest technologies and safety procedures. A strong safety culture is essential for preventing electrical accidents. This involves creating a work environment where safety is valued and prioritized, and where workers are encouraged to report hazards and near misses. Management should provide the resources and support necessary to ensure that electrical work is performed safely. Arc flash is a serious electrical hazard that can occur when a short circuit or ground fault creates a high-energy arc. Arc flashes can cause severe burns, blindness, and even death. To protect workers from arc flash hazards, employers should conduct arc flash hazard assessments and implement appropriate safety measures, such as wearing arc-rated clothing and using insulated tools. The NEC provides guidance on arc flash hazard assessments and safety requirements. Lockout/tagout (LOTO) procedures are used to prevent accidental energization of equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and applying locks and tags to prevent it from being turned on. Proper LOTO procedures are essential for protecting workers from electrical hazards. Confined space entry is another potentially hazardous activity that requires special precautions. Confined spaces are areas that are large enough for a worker to enter, but have limited means of entry and exit and are not designed for continuous occupancy. Electrical hazards can be present in confined spaces, so it is important to follow proper entry procedures, including testing the atmosphere for hazardous gases and providing ventilation. Electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents. By following safe work practices, being aware of potential hazards, and reporting unsafe conditions, we can create a safer work environment for ourselves and our colleagues. Remember to always de-energize electrical equipment before working on it, use appropriate personal protective equipment, and follow lockout/tagout procedures. If you are not qualified to perform electrical work, hire a licensed electrician. Electricity is a powerful force that must be treated with respect. By understanding the principles of electrical safety and following safe work practices, we can protect ourselves and others from electrical hazards. Consider the specific requirements for different types of electrical installations, such as those in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust are present, creating a risk of explosion or fire. Electrical equipment used in hazardous locations must be specially designed and certified to prevent ignition of these flammable substances. The NEC provides detailed requirements for electrical installations in hazardous locations. Renewable energy systems, such as solar photovoltaic, PV, and wind power, are becoming increasingly common. These systems require special electrical considerations, such as the use of disconnects, overcurrent protection, and grounding. The NEC provides guidance on the installation of renewable energy systems. Electric vehicle (EV) charging stations are another growing area of electrical installations. These stations require dedicated circuits and overcurrent protection to safely charge electric vehicles. The NEC provides requirements for EV charging station installations. As technology continues to evolve, electrical codes and standards are constantly being updated to address new challenges and ensure safety. Staying informed about these changes is essential for electrical professionals. Continuing education courses, industry publications, and participation in professional organizations can help electrical workers stay up to date on the latest developments. Electrical safety is not just about following rules and regulations, it is about developing a mindset of safety. This involves thinking critically about potential hazards, planning work carefully, and taking the time to do things right. A strong safety culture is essential for creating a work environment where safety is valued and prioritized. By working together, we can prevent electrical accidents and create a safer world for everyone. Remember that electrical codes and standards are minimum requirements. In some cases, it may be necessary to exceed these requirements to provide an adequate level of safety. Always consider the specific circumstances of each installation and take appropriate precautions. Electrical safety is an ongoing process that requires continuous improvement. By learning from our mistakes, sharing best practices, and staying informed about the latest technologies and safety procedures, we can make electrical work safer for everyone. Grounding and bonding are crucial for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. Bonding ensures that all metal parts of an electrical system are at the same potential, minimizing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding. Wiring methods are also important for electrical safety. The NEC specifies the types of wiring methods that are permitted for different applications. These wiring methods are designed to protect conductors from physical damage and environmental factors. Proper installation of wiring methods is essential for ensuring the safety and reliability of electrical systems. Overcurrent protection is a critical component of electrical safety. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect conductors and equipment from overheating due to excessive current. The NEC provides requirements for the selection and installation of OCS.